On September 23, 1999, a team of engineers at NASA's Jet Propulsion Laboratory was waiting for a signal from Mars. For the previous 9 months, they had been guiding a spacecraft called the Mars Climate Orbiter through hundreds of millions of kilometers of empty space. It had survived the launch. It had crossed the solar system. It had reached Mars almost exactly when planned. Now all it had to do was fire its engine, pass behind the planet, and enter orbit. Mission Control watched as the spacecraft approached Mars. Then, right on schedule, its signal disappeared. This was expected. The spacecraft had moved behind the planet, temporarily blocking communication with Earth. The engineers waited for it to appear on the other side. A few minutes passed. Nothing. They waited longer. Still nothing. The spacecraft never called home again. Somewhere behind Mars, a machine that had taken years to design and millions of dollars to build had simply vanished. At first, nobody knew why. The rocket had worked. The engine had fired. The spacecraft had followed its instructions. There had been no obvious explosion, no dramatic mechanical failure, and no final distress signal. But when investigators began examining the mission's calculations, they discovered an error so simple that it sounded like a joke. One team had used metric units. The other had used imperial units. And because nobody caught the difference, NASA's spacecraft had flown directly into the Martian atmosphere. The Mars Climate Orbiter was supposed to become one of NASA's most important spacecraft around Mars. Its job was to study the Martian atmosphere, monitor the planet's weather, and help scientists understand how Mars had changed over time. It would measure temperatures, observe clouds and dust storms, and search for signs of water and climate activity. It also had another important responsibility. A second spacecraft, the Mars Polar Lander, was scheduled to arrive a few months later. Once the lander reached the surface, the orbiter would help relay communications between it and Earth. The two machines were part of an ambitious plan to explore Mars more frequently while spending less money. NASA called this new philosophy faster, better, cheaper. Instead of building one enormous spacecraft over many years, NASA wanted to launch smaller, less expensive missions more often. In theory, it was a clever strategy. But building complicated spacecraft faster and with smaller teams also meant there was less room for mistakes. The Mars Climate Orbiter launched from Cape Canaveral on December 11, 1998. After separating from its rocket, it began a journey lasting more than 9 months. The spacecraft was not flying in a perfectly straight line. Earth and Mars were both moving around the Sun, so engineers had to predict where Mars would be months into the future and guide the orbiter toward that exact location. It was like trying to throw a dart at a target while both you and the target were moving thousands of kilometers per hour. To remain on course, the spacecraft occasionally used small thrusters. These thrusters were not always making huge, obvious changes. Many of their firings were extremely small. But in space, even a tiny push can become important. There is almost no friction to slow a spacecraft down. A small error introduced today can continue affecting its path tomorrow, next week, and months later. That meant NASA's navigation team needed accurate information about every force acting on the orbiter. Every thruster firing. Every adjustment. Every tiny push. This information came partly from software developed by engineers at Lockheed Martin, the company that built and operated the spacecraft. The software recorded the force produced by certain thruster firings and sent that information to NASA's navigation team. But there was a problem. The Lockheed Martin software reported the force in pound force seconds, an imperial unit. NASA's navigation software expected the numbers to be in Newton seconds, a metric unit. The number arrived. The navigation software accepted it. But the two systems did not agree about what that number actually meant. 1 pound force second is approximately 4.45 Newton seconds. That is not a tiny difference. Imagine ordering 1 kilogram of something and receiving more than 4 kilograms instead. Now imagine making that mistake repeatedly while guiding a spacecraft toward another planet. NASA's navigation team believed the thrusters were producing less force than they actually were. Each individual error appeared small. But the mistakes accumulated throughout the 9-month journey. Thruster firing after thruster firing, the spacecraft's calculated location moved further away from its real location. On computer screens in Mission Control, the orbiter appeared to be following one path. In reality, it was following another. And there were warning signs. As the spacecraft approached Mars, members of the navigation team noticed that its predicted position was behaving strangely. Different tracking methods did not agree with each other. The spacecraft appeared to be drifting. Engineers performed corrections, but the unusual readings continued. Some members of the team became concerned that the orbiter might pass dangerously close to Mars. There was even a request to collect additional tracking data to better understand what was happening. But the concern was not handled with the urgency it deserved. Communication between different teams was poor. Some problems were discussed informally instead of being documented through the official reporting system. Responsibility was divided between NASA, the Jet Propulsion Laboratory, and Lockheed Martin. Each group was working on a different part of the mission, and no single person had a complete view of every warning. The teams were also working under pressure. The spacecraft had been designed as part of NASA's faster, better, cheaper era. Budgets were tight. Staffing was limited. Schedules were demanding. Engineers were preparing for the Mars Climate Orbiter while also supporting the Mars Polar Lander mission that would follow it. The unit error was the technical cause of the disaster. But the real failure was much larger. The software requirements said that the data should be metric. The data was not metric. The mistake should have been discovered during software reviews. It was not. It should have been caught during testing. It was not. It should have become obvious when the navigation data began behaving strangely. It did not. And even when engineers raised concerns, the system failed to bring the right people together in time. By September 23, the orbiter was closing in on Mars. The spacecraft was supposed to pass the planet at a safe altitude and use its main engine to slow down. Mars gravity would then capture it into orbit. The planned path would bring the spacecraft to roughly 226 kilometers above the Martian surface during its closest approach. But because of the accumulated navigation error, investigators estimated that the real trajectory was approximately 170 kilometers lower than planned. Instead of passing safely over Mars, the spacecraft may have descended to an altitude of only around 57 kilometers. That was deep inside the Martian atmosphere. Mars has a much thinner atmosphere than Earth, but at that speed, even a thin atmosphere can be deadly. The orbiter was not designed to survive atmospheric entry. As it passed behind the planet, it may have experienced intense heat and aerodynamic forces. It may have broken apart. It may have burned up. NASA's investigation considered the possibility that it could have skipped back into space. But it was never found. From the perspective of mission control, there was no visible disaster. There was only silence. The signal disappeared approximately 49 seconds earlier than expected. Then the scheduled moment for the spacecraft to return passed. Engineers searched for it using NASA's Deep Space Network. They listened at different frequencies. They sent commands. They considered whether the spacecraft had entered the wrong orbit or switched into a protective safe mode. But no answer ever came. The Mars Climate Orbiter was gone. NASA's press materials valued the orbiter's spacecraft development and mission operations at around $85 million, not including its launch. The larger Mars Surveyor 1998 program, which included both the orbiter and the Mars Polar Lander, cost more than $327 million. But the financial cost was only part of the loss. Years of scientific work had vanished. The spacecraft would never study the Martian climate. It would never photograph the planet's atmosphere. And it would not be there to relay signals from the Mars Polar Lander. When the investigation report was released, the unit conversion became the headline. Metric versus imperial. Newtons versus pounds. It sounded like one careless programmer had typed the wrong measurement into a computer and destroyed a spacecraft. But that explanation is almost too simple. Engineering mistakes happen constantly. People misunderstand instructions. Programmers write imperfect code. Numbers are entered incorrectly. The purpose of reviews, tests, and communication procedures is to stop one mistake from becoming a catastrophe. The Mars Climate Orbiter was not lost because one human being made one error. It was lost because every layer that should have caught that error failed. The requirements were not followed. The software was not properly verified. The navigation differences were not fully investigated. Concerns were not communicated effectively. And the spacecraft was allowed to continue toward Mars while the teams responsible for it held different versions of reality. One version existed inside NASA's computers. The other existed in space. By the time everyone understood the difference, the spacecraft had already disappeared. The disaster forced NASA to examine how its teams communicated and how mission-critical software was tested. It became one of the most famous engineering failures in history, taught in universities and companies as a warning about assumptions. Never assume that another team uses the same system you do. Never assume that a number means the same thing to everyone who reads it. And never ignore a small inconsistency simply because the larger system appears to be working. Because the Mars Climate Orbiter worked almost perfectly. It launched successfully. Its solar panels deployed. Its communication system operated for 9 months. Its computers responded to commands. Its engine fired when instructed. It traveled hundreds of millions of kilometers and reached another planet. And then, during the final few minutes, years of work were destroyed by an error that could have been corrected with a basic unit conversion. Not a mysterious force. Not an unpredictable storm. Not an alien environment no one could understand. Just two teams using two different definitions for the same number. The Mars Climate Orbiter did not miss Mars by millions of kilometers. It reached exactly the place it had been sent. The problem was that the engineers had unknowingly sent it to the wrong place. And somewhere in the silent atmosphere of Mars, a spacecraft disappeared because one number meant pounds to one team, and newtons to another.